So now we are in the transient stability. Transient stability, usually we don't have any applications as per your syllabus. We don't have any applications in the regarding the transient stability analysis, but we'll try to study a very important application. And that application is, for example, I'm taking one condition. One condition is nothing but a synchronous generator. For example, just try to take one condition. One condition is a synchronous generator. Okay, so this is actually a synchronous generator. Which to this synchronous generator, we have connected one transmission line. Okay, and we have connected one transmission line, not one transmission line, but two transmission lines. That is nothing but which it is a parallel transmission line. After that one, we are going to connect to infinite bus. We are going to call it as it is connected to some infinite bus or load. This like this. Okay, this is one condition. Okay. This is actually a network. So for this network, what happens? For this network, this is actually the shaft power. Okay, and this is the electrical power which it is going to deliver to those two transmission lines. Okay, so this is the shaft power. I'm going to call it as a PS, and this is the electrical power. I'm going to call it as a P. Okay, so PS shaft power, or in some textbooks is going to notate it as a PM, that is the mechanical power, because shaft power or the mechanical input to a generator and electrical output which is going to come out of the generator, right? So this electrical output is going to be received by these two transmission lines and it is going to give to the infinite bus, right? So now what happens for this common condition, that is we have a reactance here. You can consider this as a reactance. We also have another reactance here, the transmission line also X reactance. So for this reactance, what is usually the formula? So if I want to write what is the electrical power is equal to E, that is the excitation voltage of a generator, and V, terminal voltage, divided by so this X is the X equivalent, because we have the two reactances here, so two transmission lines which are connected in. And after it is also depending on sine delta naught is an initial angle. For this one, I'm going to draw here curve. See clearly, we have a curve here. So this is the power angle delta. So this is the angle delta, and this is the power P. Okay. So first of all, I have already told that we have a PS here. PS is nothing but shaft power, which it always remains a constant. So this shaft power is always remains a constant. It is not possible to vary this power. Okay. So we are assuming this shaft power is always remains constant, and this is a shaft power. Next, I need to draw the electrical power, right? So for this electrical power, I'm drawing this electrical power. This is an electrical power. So this electrical power is in a sinusoidal because P is equal to EV by X equivalent sine delta naught. So sine delta naught means this is the amount, this is the point at which angle is a delta naught. Okay, this is the angle which it is a delta naught. So I'm writing this angle is a delta naught. Delta naught is an initial angle, right? So at this condition, what it is exactly, in this condition, I will write here, in this condition, PS is equal to P. So at this condition exactly, right here, PE is equal to PS also, because P is always varying. No? So the electrical power is equal to the shaft power. So this is it is running perfectly under stable condition. We have a generator and we have a reactance parallel transmission line. We have connected to a load. So everything is running perfectly. Okay? So now what we are going to do is we will do one thing. So what we are going to do, we will do fault. That is, we are going to apply a fault on any one of the transmission line. Okay? So I'm going to write this as PE, that is the electrical power before fault. I'm going to write this is electrical power before. So this is the curve. So now what happens? Now there is a fault is going to take place on a transmission line. So when the fault is going to take place on this transmission line, there is a severe fault or three-phase fault is going to take place on this transmission. What happens? Whatever the circuit breaker here, it is going to trip. This circuit breaker is going to trip this line out of the system. So now what is the different condition? Now this is not X equivalent. Now the X equivalent is going to be increase. See here, X equivalent is going to increase. What is the previously X equivalent? Previously X equivalent is equal to just X divided by 2. Is this right? Equivalent is equal to X by 2, because in the previous condition X and X are going to connect in parallel. So therefore in the before fault conditions X equivalent is equal to X by 2. So if you are substituting this one, then you are going to get the electrical power. That electrical power is this, where the electrical power is equal to the shaft power. Now there is a fault is going to take place on any one of the transmission lines, that is in the line 2. Therefore the circuit breaker is going to make this transmission line out of the system. So when the circuit breaker is making this transmission line out of the system, now what happens to the reactance? Now this X equivalent is nothing but I'm going to write this as an X equivalent to is nothing but only X, because we have only one transmission line left in the system. The transmission line reactance is only X. So that is this value of X. That indicates if you compare this to what happens, X is increasing. So X is increasing from X by 2 to X. That means this X equivalent is increasing. So when this X equivalent is increasing, what happens to this electrical power? Electrical power will decrease, right? The electrical power will decrease. So now I need, but whereas this PS will be always remains constant, okay? Because within this fraction of time, it is not possible to make the PS to be changed. So we are always assuming this PS as a constant, okay? So therefore what happens, this electrical power is dropping. Now this is not the curve. Now if this is the maximum power in the previous case condition, now the maximum power will reduce, right? And this electrical power is going to reduce. Now I'm going to draw another curve. Okay, this is the new PE. We are going to call this is also a PE, but after the fault, because after fault we have left with only one transmission, and for that reason the electrical power have been come down. Now, so what is the analysis? So this is actually I'm indicating the point A. I'm assuming this point as A. This point as A point. Here at this point A, it is running under the stable condition, but whenever the fault is taking place, what happens to this value? Now this value will come drop to here. So it will come to this point. I'm going to assume this point as a B. Are all of you understanding the logic? So whenever the fault is taking place, whenever the fault is taking place on this transmission line, on any one of the transmission lines, so what happens, the X equivalent, that is the transfer reactance, have been increased. So therefore the electrical power have been decreased. So this is actually the new electrical power curve. So this is the after fault condition. So what happens now, and when the fault is taking place, now it is moving, the electrical power is moving from this position to this position. What is this position is exactly now? It is not P is equal to PS, but this is PA is less than PS. Or you could also able to write it as PS is greater than P. Both the conditions are correct. Now in this condition, PS is greater than P. So when the PS is greater than P, what is the equation? What is operating power? PS minus P. So in this condition, now PS is greater than P. So when the PS is greater than P, what happens? This one will give now positive, right? Indicates it will start. It will start accelerating. So in the practical condition also, I will say, whenever the electrical power is reduced, if you have a speed of a rotor, just assume the speed of a rotor. So whenever the load is reduced, because one transmission line is reduced, automatically the load is going to reduce. So whenever the load is reducing, what happens? The speed will increase. So this indicates this one. So I can write here as omega, or omega is greater than omega s. Omega s is a synchronous speed. This condition, omega is equal to omega s. Please consider the 2 points. I'm repeating again. At the position A, it is going to run at synchronous speed, and electrical power is equal to the shaft power. So until there is no disturbance is going to occur. So when the disturbance came, that is when the transmission line is out of the system. Now what happens? The PS is greater than PA because PA have been dropped, and omega is greater than omega. That is more acceleration. So when it is getting acceleration, what happens to the angle? Angle will also increase. So angle will increase, and that means it will not come to this x-axis because it is delivering some amount of electrical power. In the previous case, it is not happened because it is completely out of the system. But here we have one transmission line. There is some power is delivering through the load. Only one transmission line is out of the system. So the delta naught will increase. The delta naught will increase, and delta naught will increase. Okay, it will increase. It will increase. So actually, it should need to come to this point. It should need to settle back to this point. Okay, so it should need to be settled back to this point, but it is not settling back because of the inertia of the rotor, or because of the kinetic energy stored in the rotor. When the omega is equal to omega is greater than omega's condition, it is not going to settle here, but it will move beyond this one. Okay, and this one we are going to call it as, okay, it will come here. This one we are going to call it as delta max. Okay, this is the maximum angle where it could able to move. Okay, where the PE value is going to able to move, that is the delta max. That is the maximum angle, and that indicates the maximum power. Okay, so we will try to assume this is this value. Then what happens? Okay, it is coming here. So when it is coming here, what is this value is now? Now PS is less than P, right? Indicates P is greater than PS. So at this condition, what happens to this accelerating power? This accelerating power now it will become negative. So when it is becoming negative, which indicates that it is going to decelerate. Deceleration means what happens to the delta? Delta value will decrease. So I'm repeating again, when it is going to get accelerate, when it is getting accelerated, the delta value will increase. When it accelerated, delta value will increase. When it is getting decelerated, delta value will decrease. So now delta value should need to decrease. So it is going to decrease. So it will decrease, it will decrease, it will decrease. And it will come to this point. It will not come to exactly B. It will come to one point, and again it will come to here, it will come to here, it will come to here, and it will oscillate, and it will settle back to this point. This point is where omega, where PE is equal to PS, and also omega is equal to omega s, right? This angle is called as a critical angle. Delta 1 are also going to call, or we can also going to call it as a critical clearing angle. Okay, delta. We have three angles. One angle is a delta naught, which is going to start at the point, and another angle is a delta maximum, which is going to move it to the maximum value, and delta C, which is going to the critical clearing angle. Okay, where it is going to settle back to the system. So these are the three angles which we are going to use to find out this critical clearing angle. The critical clearing angle is this one. We need to derive this one. Okay. So this is one example. So now if you want to calculate the area, this is the calculated area of A2. This is A2. Okay. This is A2 and this is A1. Okay, this is area A1 and this is the area A2. So now you need to compare these two areas. Okay, if these two areas are equal, then we are going to call the system as stable condition. That is A1 is equal to A2, then we are going to consider the system as a stable condition. If these two is not equal, then we are going to call the system as an unstable conditions, right? Okay, this is one example how we are going to use the graphical method and how we are going to use, how we are going to say either the system is stable or not. Okay, so when PS is greater than P, we also have here the value, that is the speed, will be less than omega s, right? Because when the PS is less than P, or when the P is greater than PS, what happens? Omega will be less than omega, so that is indicates deceleration. The speed will be get decreases. Okay, so these are the three conditions, and it is not going to get settled back at the same time. It will take so much of oscillations. So from B, it is going to achieve this point. I am going to call it as a point C. Well, it will come from A to B, then it will move to this C, and again it will settle back to the point D. Okay, I'll try to zoom here. If you see here, we have a point A where the P is equal to PS. Okay, where the synchronous machine is running at the rated speed, that is synchronous speed. Now what happens when the fault have been taken place? It is going to move to the point B. So when it is going to the move to the point B, at that time the PS is greater than PE, because if you see here, this is the PS curve and this is the PE curve. So P is greater than PE, therefore omega is greater than omega s. So when the P is greater than P and omega is greater than omega s, what happens? It will move. Now this, what happens? This in this case, the delta will start increasing. So when the delta is starting increasing, it should need to increase through the curve only. So it is going to increase, it is going to increase, and it is going to increase, and it will stop at a point C, position C. So that angle is called as a maximum angle. Then after what happens? So at this condition, omega is less than omega s and PS is less than P. So at this condition, what happens? It will start decelerating, because in this case PS is less than P, which it will give you a negative value. It will start decelerating, means delta angle will decrease. So delta angle will decrease, and it will decrease, and again it will increase, and it will decrease, again it will increase, it will decrease, it will increase, it will decrease, it will increase. So at one point it is going to settle back. That point is a critical clearing angle point, and where the P is equal to PS again and omega is equal to omega s again. If you see the two conditions, the first condition is at the position A, and the second condition is at the position D. At position A, omega is equal to omega s, P is equal to PS. At the position D also, omega is equal to omega s, P is equal to PS. Okay, so until it is going to come to this point, we could not able to say that the system is stable or not. Okay? So this is the thing. If I want to draw this transients, so if you see here from B to C, C to E, we are getting oscillations. No, those oscillations are nothing but unlike this one. If I want to draw only the delta, that indicates what it is oscillating. Only delta is oscillating from here to here, here to here, here. That indicates at this one point, and again, what happens? It will oscillate, 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 and settle at another delta angle. That is this delta. This is a delta C, critical clearing angle, and this is a delta naught, the initial angle. Right? So these oscillations are nothing but on here it will take place, and it will settle back to the system. Okay. Okay, this is called as one. We took one application. This is an equal area criteria method. How they are going to do? Okay. Okay. This all depends on the system. For example, if it is going to cross this maximum value, I have already told it is not crossing this 90 degrees. You see clearly it is not crossing the 90 degrees. If this delta maximum value or this the critical clearing value is crossing the 90 degrees, what happens? These areas will not be same. So then that indicates that C, if it is not settling to C, for example, if it is moving up to here, if it is moving up to here, what happens? This area is different. This A2 complete area will be different, and this area A1 is very less. So that indicates it is an unstable system. Okay, that completely depends on the inertia of the rotor of the synchronous machine. So it is completely mainly depends on the inertia. Okay, inertia. Inertia of the rotor. Okay, how much it is going to store the kinetic energy, how much it is giving up the kinetic energy. Okay, that is the basic operation of a synchronous machine. Okay, so this is one application. So in the class notes, what I have given you in the class notes, I took another example, but that example may confuse you because that example is not recorded in the synchronous generator. but that example is regarding the synchronous motor. You see, swing equation, equal area criteria, and this, if you see clearly, this is actually sudden increase in the mechanical load of a motor. Okay, this is not a generator, this is a motor. Whatever you have studied now in case of a generator, that is actually the opposite operation of a motor. Okay, just it is an opposite operation, because what is the input of a motor? You see, just I will draw here. For example, if you have a motor, if you have an AC motor, which it will give you, which you are going to give you the electrical energy, but it is going to provide you mechanical energy. So in this case, what is the accelerating formula? Accelerating formula is different, because this is a motor. Because this is a motor, then the accelerating formula will be different. This is a synchronous motor only. Synchronous motor. Equal to E minus PS. Because it is a motor where the mechanical load is going to change, where the load is changed, that is the mechanical load is going to change, but the electrical power will remain constant. So this is actually the PA is equal to P minus PS in case of a motor. This is in case of motor. Okay, so this is actually application. This is for your better understanding purpose. We have discussed. This is not there in your syllabus, but you need to understand how we are going to use the equal area criteria. If he is giving out of the syllabus, or if he is asking also the application of the equal area criteria, means you can discuss this as one example. Okay, you can discuss this as your one example. Okay. If you wish to discuss also this motor, means we'll discuss also this motor also. Okay. The condition, that is the positions, the torque angles, the speeds, the power, acceleration or deceleration, everything is there. We have discussed here in every condition in this diagram. How we are going to discuss in every condition in a diagram. The similar thing we are going to discuss in case of a motor. That's it. See here the condition, how the delta is varying, and how, what is the condition here at point A, what is the condition at point B, what is the condition at point C, and what is the condition again at point D. Okay. So this is the analysis of the synchronous machine using equal area criteria method. So this is applicable only for single machine or a two machine system. It is not going to applicable for more than two machine system. For that reason, we are using the point by point. So in the next class, we will try to discuss about this critical clearing angle, how we are going to derive this critical clearing angle. Okay. And also the point by point. Okay. So whatever you have doubts, please ask me now. I think we are reaching to 10:20. Please, whatever you have doubts, please ask me in the chat box. See, whenever by mistakenly, if you are annotating, that is the process. What you're drawing anything, or if you are moving your mobile, or if you are touching any screen, you will have an option that you need to clear, or you can able to delete. Okay, for that reason, I have waited for 1 to 2 minutes that you are going to delete or not, because it is not possible to tell in the screen, because it is completely covered with that black lines, right? See, if you see here, so we are at this complete part. So we have completed. We have considered one application also. Next, we will discuss about the critical clearing time, and also we'll discuss tomorrow. So we'll try to discuss about the critical clearing angle. Then after, in the next class, we'll try to discuss about the methods to improve the transient stability, and the last one is point by point method. Okay, so this is completely concept only. If you try to, please try to read all the concepts, all the units perfectly. Whatever you have doubts, you can ask me or you can message me. You can also make me a WhatsApp call so that I will respond you. Please don't waste your time. Please try to utilize your time. I think after completion of this April 30, which you already know, after completion of that April 30, or when the lockdown is completely over, they may give you directly to the exams itself, that is mid exams, and directly the external examinations will be there. And after external examinations also, there will be no holidays, I think. Okay? Please try to prepare now itself. There will be no preparation holidays also. Please try to be prepared now itself. Okay. Okay. Who can send me the attendance? It is 10:21 and. Okay. Okay. Nikhil, send me the attendance. Okay. Okay. Thank you all of you. And